Well, welcome back. This is Mrs. Hanson, and we're picking up in our next lesson in our radical reactions chapter, looking at a specific example called the chlorination of methane. And as we begin thinking about the radical mechanisms that were presented from our last section and applying them to this specific example, we're going to focus in on the three major steps for any radical reaction to begin, to propagate, and to terminate. So here is an overall equation. This overall equation represents how reactants turn to products. And a lot of things happen along the way in terms of mechanism. So we have our simplest hydrocarbon, a methane molecule, composed of a central atom of carbon and 4 single bonds. Sitting on top of the arrow, of course, is molecular chlorine, Cl2. Those two atoms are held together by a single covalent bond. Notice that on the arrow we have an energy. Remember that energy is defined as Planck's constant times the frequency. So when you see H nu sitting on the arrow, it's another way of just representing that there's an input of energy, typically from sunlight or from heat. And now on the opposite side, the product side, we have substituted out one of the hydrogens, and a chlorine has been attached. And of course, now the hydrogen has gone to the Cl. So in this substitution, it appears as if the H and one of these Cl's have just switched places. So how does this happen? It's our first example of a specific radical reaction. Well, these steps in a radical mechanism take place in three categories. 3 different steps are always involved in this mechanism. We need to initiate the radicals. We then propagate to create the desired products, and then we terminate the last step to get rid of the radicals. So that's the order. Initiation creates the radicals. We then propagate, which is the most important steps, and these steps are responsible for the observed reaction. They're the reactants turning to desired products, and once those desired products are achieved, we need to terminate the reaction, and that means to just destroy the radicals to stop the propagation process. So with those in mind, let's begin examining the mechanisms for the chlorination of methane. We mentioned that the very first step is called initiation, and this is where the radicals are created. One of the most common ways of creating a radical is through homolytic bond cleavage. Recall that was the very first mechanism of the 6 that we studied in the last section, and that means we're going to break a bond. And notice that these 2 electrons that were a shared pair have each gone their separate ways. So I have 1 green electron on each of those 2 radicals of chlorine. A homolytic bond cleavage is an example of an initiation step in which radicals are made. So that's the key there. In initiation, we have to create the radicals. Once those radicals are created, we see the propagation steps, and usually this is a series of at least 2 steps in the propagation. So these steps are self-sustaining. They will continue for as long as the radicals are available. So the radicals that we produced begin then propagating, and let's take a peek at the first of these 2 steps. Notice here we have a bond and a methane molecule, and I'm just going to color code these blue. These 2 blue electrons are in a shared pair between the carbon and the hydrogen. The radical that we made above now serves as a reactant in the first propagation step. Notice we have 3 fishhook arrows representing a hydrogen abstraction. This bond is broken, and a new bond is forming between the H and the Cl. So color coding, the blue electron, one of them remained on the carbon. A blue electron now remains there on the hydrogen, and if we color code this electron red, we can see where it landed in this new bond. So a hydrogen abstraction forms a carbon radical in the first propagation step. Again, the presence of a radical then becomes the reactant in the next propagation step. So remember, what we make and then use is known as an intermediate. We keep generating radicals that will propagate this reaction over and over and over. So the first step, a hydrogen abstraction. The second step, we see a halogen abstraction. Now we're back to molecular chlorine. Molecular chlorine has a shared pair of electrons. Remember, up on the arrow, we had molecular chlorine. The initiation step created radicals. These radicals then became the first reactant that was used and then regenerated. So the molecular chlorine plays a role here in terms of the halogen abstraction. So we have a lone electron on this carbon radical and a shared pair between the chlorine. We can see 3 fishhook arrows where a new bond is made and a bond is broken, regenerating the chlorine radical. We have placed a halogen onto the methyl group. And remember, this was our desired product, methyl chloride. Notice then that we can still keep propagating. This new radical of chlorine has been remade, and I can continue step 1 and step 2 over and over and over. They propagate until we destroy those radicals. And in a termination step, the purpose there is to stop the reaction, and we do so really by the opposite of the initiation step. If the initiation step was homolytic cleavage, the termination step is the coupling to where the radicals went back to molecular chlorine. So destroying the radicals stops the propagation step. We could destroy the radicals that were made from chlorine. We could destroy the radical that was made from the carbon as well. So there's some options here of what radicals that were produced in that propagation step that could be coupled to eliminate the reaction from occurring any further. So we could couple the molecular chlorine. We could couple the radicals of the carbon radical and the chlorine radical, or we could actually form an ethane molecule and destroy the carbon radical by just hooking those together. All you need is one choice. This particular equation has 3 opportunities of what you could couple together to destroy the radicals. It's just important that we pick one of the 3. Not all 3 need to be presented. So again, 3 steps. Initiation, we create the radicals. Step 2, propagation. These are self-sustaining steps in which a radical is used, and then so we use it in the first step. It comes back in the last step. The radical that is produced in the first step is then consumed in the next step, and you can begin to see the overall equation when you cancel these out. What's made and then consumed does not appear in the overall equation. We see the overall equation where we have CH4, molecular chlorine on the left side of the arrow, forming HCl and methyl chloride on the right side of the arrow. So the overall equation is found in the propagation step. And then we terminate the radicals to stop the propagating. So that sum of the propagation steps is reminding us of what we call the net equation, getting rid of what was made and consumed on both sides of the arrow. So getting rid of anything that appears on one side would cancel the other. The chlorine on the left cancels the chlorine on the right. The carbon radical cancels on the right with the left, and we come up with the overall equation. And this occurred through a radical mechanism. So this, remember, the propagation is a chain reaction, and it keeps going and going and going until the reaction is stopped with the termination step of destroying the radicals. This propagation is actually difficult to control, and oftentimes you could see polychlorination occurring. Methyl chloride is more reactive towards radical halogenation than methane. So in other words, if we think about what this is saying is, here is a methane molecule. Notice these are all hydrogens. In the presence of molecular chlorine, that's a Cl-Cl single bond, and an energy to activate, we create a radical, and we chlorinate the first position of a CH bond, and then we can chlorinate the next and a third and all four. So how do we control this? It's very difficult. So if we say we want to produce just methyl chloride and stop the reaction from proceeding to keep going, the little trick is to just really use excess methane and small amounts of chlorine to encourage monochlorination. Excess methane and a very little bit of chlorine to stop the reaction with a single substitution there, although it's very difficult to control. Let's practice together and try drawing a mechanism for the radical chlorination of methyl chloride to produce methylene chloride. So notice what we're starting with. We already have one chlorine in position, and we're adding the second chlorine. So remember the three steps. We need to draw an initiation step, we need to draw the propagation steps, and then finally at least one of the possible termination steps that destroy the radical. So we need to create the radicals. The last step destroys the radicals, and the propagation step creates the overall equation. So let's begin by taking that molecular chlorine, a Cl to Cl, and the first initiation is bond cleavage. So we would form, let's say if these were two red electrons, breaking the bond with two fishhook arrows goes on to support two radicals of chlorine. So there's my first step, the initiation process. On the arrow, we'll need to show energy because that's not a spontaneous process. It needs to have an initiation. You might also see some heat. Either way, you have to force that bond to break. Secondly, we need to show the reaction occurring, right? We want to create dimethyl chloride. So let's begin by writing out the initial reactant, which had one chlorine, and now it's going to react with the radical, one of these radicals that we just produced up above. Which hydrogen is going to be abstracted? Well, let's just focus here. I have 3 equal choices. I'll just pick the bottom hydrogen just based on location there. And I know that this sigma bond, this single bond, one of these electrons is going to reach out and form a new bond with the chlorine radical. So I can see a new bond forming HCl. And what also has formed with the third fishhook, the second electron collapses back onto the carbon, and we create a carbon radical. And the lone electron now is on the central carbon. In the next step, the radical that we just produced becomes the next reactant. It's about to get consumed. Radicals are made and then consumed in the next step. Remember, this next step involves molecular chlorine, Cl2. It's part of the overall equation, so it must appear in the propagation step. The radical chlorine has a bond that's going to be broken, a halogen abstraction. So just think about color coding your electrons. The electrons in the chlorine, one of them is going to reach out to form a bond to the carbon. The electron here is going to reach out to form a bond to the chlorine, and this electron is going to collapse back onto the chlorine to make a radical. So we have formed the original molecule now with the additional chlorine and have regenerated the chlorine radical from our first step. Now, if we think about what we've done, the initial reactant, methyl chloride. On the second, we had the initial reactant of molecular chlorine, and that's written here. On the product side, we see HCl, that's here, and now we have produced the dichloromethane, which is also represented. And what's canceling are the radicals that were made and then consumed along the way. So this was a two-step mechanism. We also need to show some sort of mechanism that's going to destroy the radicals. You just have to pick one termination step. Probably the easiest to draw is to just consume the chlorine radicals. That way I don't have to draw the larger structure of the methane. And so I'm just going to undergo coupling, those two fishhook arrows that go back to produce the diatomic molecule of chlorine. So this is our termination step, is destroying the radicals. So let's compare what we've drawn and just reiterate the steps for emphasis. Number one, initiation. Initiation created the radicals. We did so by a homolytic bond cleavage and created two radicals of chlorine. In the propagation step, we had step 1, where hydrogen abstraction occurred, and step 2, we had a halogen abstraction occur. Notice that the first radical that is made is then consumed in the next step. The radical we initiated with is brought back to us in the last step, so the reaction can propagate over and over and over until we destroy the radical. And in this operation, the radicals were destroyed by taking a carbon radical and a chlorine radical and forming the product. There were 3 choices. It doesn't matter which one you draw, you just have to find a way to destroy in a termination step any radicals by forming the original bond back. So that's it. We have 3 steps in a radical reaction: to initiate, to propagate, and to terminate. These radical initiators require energy to initiate that chain reaction. And so typically, you're looking for these initiations to have weak bonds that cleaves homolytically rather easily with heat or light. Of course, we see the triangle on the arrow for heat, and H nu, that's the energy of a photon. Dihalides, such as chlorine or bromine, make great initiators. They're easily broken. Alkyl peroxides also contain a bond that's broken even easier. And acyl peroxides are the easiest to break of all. And notice that this bond dissociation energy, the amount of energy needed to break a bond, here's the dihalides of a chlorine at 243. Lower energy in alkyl peroxide, and even lower than that is an acyl peroxide. Notice this carbon is attached to a carbonyl oxygen as well as the oxygen. So we see an electron withdrawing in both directions, making this bond very easy to break. So these are examples of the types of molecules we use to initiate reactions in a radical mechanism. On the opposite end of the chain, we need to stop or terminate, so we look for radical inhibitors. These radical inhibitors react with radicals to stop the chain from propagating. Oxygen is a very stabilized radical, and compounds that are easily formed and stabilized are good inhibitors. So this is usually how we see molecular oxygen drawn. It has a double bond so that each complete an octet. So just good old molecular oxygen. But rearranging those electrons to create just a single bond creates an oxygen radical, which makes a very good inhibitor. So that stabilized radicals as a diradical, and that just simply means, notice that each of those oxygens has a lone pair. So it can react with two other radicals and take that as a termination step. Hydroquinone is also a reactant with two radicals. And what we look at is that oxygen, in the presence there of radicals, stops the termination step from occurring. And this is the how part that occurs. Here's this hydroquinone. It has a benzene ring with two hydroxyl groups in the para position. So 1,4-dihydroxybenzene, hydroquinone. And here we have a carbon radical. And in the presence here, this hydroquinone forms just through resonance stabilized, and again, you can see in the allylic position, it would be resonance stabilized, an oxygen radical. And what's happened in that hydrogen abstraction, this hydrogen, this bond here, was cleaved. So we see an RH has formed, and this oxygen radical then serves in the termination step, and we can see how then, and this is kind of a nice situation, this hydrogen here then can also be cleaved and create two oxygen positions that is resonance stabilized and can go on then to terminate a step, to get rid of a radical by coupling with it and taking it out of the propagation. So by having two oxygens, either in a hydroquinone or just molecular oxygen, we have an opportunity to have two sites of termination occur. But what we're saying is that's a good way to end a reaction, is placing in an oxygen compound, because it will take out radicals very quickly. When we think about halogenation and how it occurs, we're going to consider thermodynamics in our next section. Halogenation, we know that can involve fluorine, chlorine, bromine, and iodine. All of them are the diatomic molecules that have a single bond between their atoms. And how much energy does it take to break those bonds? Well, look at the number there for fluorine, negative 431. That's a very exothermic process. So much so that so much energy is released, it's actually quite violent. It's so exothermic, it's not practical to fluorinate a carbon-hydrogen bond. This guy on iodine is endothermic and occurs so slowly. Look at the positive value. So iodination is endothermic and therefore not thermodynamically favored, and it's so sluggish, we just say it does not occur. That leaves two halogens that are thermodynamically favored for radical mechanisms, chlorine and bromine. Notice that chlorine is far more exothermic. Bromine is still exothermic, but not nearly as violent, right? Not nearly as much energy is released. So let's take a look then at what that means in terms of reactions. We can see that fluorine is too violent. We see that iodine is too sluggish, and therefore we conclude that the only useful halogens for a radical mechanism are chlorine and bromine. But let's compare their thermodynamics and understand that they really react very differently in terms of selectivity. Both chlorination and bromination are exothermic. That means both will occur. They're favored exothermically, releasing energy. In the first propagation step, a hydrogen is abstracted. So that's this bond here. And we could see that that would be 3 fishhook arrows. The hydrogen reaches out. The electron from hydrogen reaches out. And this bond will then collapse right there to make the carbon radical. And now we have created a new single bond, HX. If X is chlorine, it's negative 21. And if X is bromine, it's positive 42. Now notice that. In the first propagation step, chlorine is exothermic. But in the first propagation step, bromine is actually endothermic. Think about what that would look like on your graph. Endothermic means I have a higher energy at the end. That would be the bromine at the first step. And then in terms of chlorine, you have an exothermic first step. The second propagation step is the halogen abstraction. That means I break this bond and we have a homolytic bond cleavage. One of the electrons reaches out to form a new bond with the chlorine, and the second one will collapse back onto the next halogen. Notice that in the first step, if it's chlorine, it's negative 96, so this is exothermic. And in the second step for bromine, this is also exothermic and pretty close to the same value. So thinking that through, if this is chlorine, the next step is also exothermic. So the reactants are of higher energy than the product. And for bromine, it's exothermic, so we end up at a lower energy state. And remember, bromine is exothermic overall, so initial to final still has to have a difference there of a negative value. So it's exothermic overall. The key difference here is noting that the first step for bromine is endothermic. The next step is saying, oh, there's the energy release. Whereas chlorine itself is exothermic for both steps. So we can see that on the energy diagram. And this is a little better view of what I tried to draw a moment ago. For chlorination, we have the initial first step as exothermic. The difference in energy from reactant to product is a negative value, exothermic. And in the second step, we see that it's also exothermic. Comparing that to bromine, the first step is of higher energy here. So this is an endothermic process, followed by a large exothermic process to end up overall exothermic. So this means that bromine occurs much slower than chlorination. It takes a lot more energy to convince this first step to occur. The activation energy is much larger in the bromination as compared to the chlorination. Therefore, since it occurs much slower, bromine is much more selective at where it will add on to the carbon radical. Based on its thermodynamics, bromine is very selective. So how does that apply to regioselectivity? Where will the bromines add? Where will the chlorines add? So with substrates that are more complex than methane, such as propane, this is a 3-carbon chain, 1, 2, 3. So that's a propane. We have 2 hydrogens on the central carbon, and we have 6 total hydrogens that are on the end carbons. So which hydrogens are going to be abstracted? And it just depends if we're adding chlorine or bromine. And we mentioned Chlorine is indiscriminate. It occurs so rapidly that we see a significant amount of each product. I can take the hydrogen from carbon number 2, or I can take the hydrogen from carbon at the end of the chain equally. So with your propane, you have 1, 2, and then, so that's the second choice, and then 6 choices here to have a mixture of all products that could possibly form. When we see a secondary radical form, and that would be this initiation step would produce a secondary radical, that is a more stable configuration than a primary, which would occur here. So you see about a 60-40 mix. And keep in mind, this also, in terms of stability, everything happens so rapidly, you really could say it's half and half. But a 60-40, just based on stability, is probably a better recommendation. So hydrogen extraction at the secondary position has a little lower activation energy. That's going to be favored in the amount of product, about 60-40. So chlorine is not very selective. It happens so fast. We mentioned that bromination is much slower and therefore much more selective for the secondary carbon radical. About 97% is going to come from the more stable configuration and a very small trace amounts of the primary position. So the fact that bromination is more regioselective than chlorination is going to be explained by the Hammond postulate. Let's review that from an earlier chapter. The Hammond postulate is just simply reminding us that at the top of this energy hill is a transition state in which bonds are being broken and new bonds are being formed. If the transition state is closer to the reactants, as in the chlorination, this is the energy diagram for chlorination, the transition state is very close to the reactant. That tells us that the transition state more closely resembles the reactant. So that this bond, this is the carbon and this is the hydrogen that we're trying to break, forming the radical. This bond is just beginning to form. Whereas on the other side, this is the bromine thermodynamics, the transition state is closer to the final product, which means that this bond is just about completely broken and this bond is just about completely formed. Therefore, the bromination is going to resemble the products at the transition state. And this makes it very selective to add the bromine to the most stable position. And I mean that by tertiary is greater than secondary, greater than primary, and so forth. So this is indiscriminate, occurring so rapidly that the chlorination will occur from all hydrogens and get a good yield of each, whereas bromine is very selective, always adding in the greatest quantity to the most stable position. To emphasize, here we have a carbon in the center, would have one hydrogen, right? Even though it's not drawn, we can imagine our hydrogen there. And then at the end, we know that these are methane, so each at the terminal position have CH3s. All of the different places that we can see where a CH bond could be broken. Here we would notice that this would be a primary radical, and here we would have a tertiary radical at the center position. So what do we observe in terms of chlorination versus bromination? Well, clearly the tertiary carbon radical would be the most stable, and bromination is very selective. 100% of the bromine will add to the most stable radical position. That's the secondary position there on that carbon, making the tertiary radical. But this is interesting up here for chlorination. Think about what we're seeing here and why we have a 35 to 65% ratio. the hydrogen in this position that would form a tertiary radical has just one hydrogen, whereas the primaries have a total of 9 hydrogens. So therefore we would see about a 1:3 ratio. For every 1 hydrogen that was in the tertiary position, there were 9 hydrogens that were in the hydrogen. So you're seeing, that there'll be more of this primary position simply because there's more hydrogen there. So just the illustration of the difference between selectivity of chlorination and bromination. Let's practice. Let's predict the major product obtained upon radical bromination of 2,2,4 trimethylpentane. Trimethylpentane, and we're undergoing bromination. Now, bromination, I want you to think, is very selective to the most stable radical. Find the most stable radical. We have to break a CH bond to do so. So let's identify all possible positions and determine the most stable location for a radical. At carbon number 1, that's the 1. At carbon number 1, we would have a primary radical. At carbon number 2, there are no hydrogens. That carbon number 2 there is all tetravalent already, so that's not a possibility. At carbon 3, that is a secondary position. At carbon 4, that's a tertiary position. And here, all of the rest of these are primaries. So we have primary, this one is no hydrogen at all, this would be a secondary, and here is a position where we would have a tertiary, just to kind of redraw that. At this position, if I were to draw a radical, that would be a tertiary carbon radical, which would be the most stable position. I was trying to write radical. There we go. So this at carbon 4 is going to be the position in which the bromine will add on. And so we're just predicting the major product. We're really not asked to draw the mechanism for this answer. And so we'll just redraw those 5 carbons, the methyl groups put back on, and the bromine added to the original position 4. Let's emphasize those steps. The first thing we did was to determine where would be the most stable position. We found primaries, tertiary, secondary. The quaternary had no hydrogen, so we took that off the plate. And we decided the most stable configuration was the tertiary carbon radical. And again, that would be the position then where we would find the bromine add. Very regioselective for the bromine. And you'll see plenty of these in terms of trying to find the major product upon radical bromination. They'll specifically, for bromination, follow the pattern of that the most stable radical will be the position where the bromine will add to the carbon. So just thinking that through, you'll have a Br2 and probably some H nu on the arrow, and you're asked to predict. Now, where do you find the most stable configuration? Remember, this is quaternary. There's 4 bonds there already, so there's no hydrogen. That's not an option. But if I look over here, I can see a tertiary carbo radical, and I can then predict the position where it would add. There's the original methyl groups and the bromine adding on across that bond. And you'll see that case occur. And you can practice those in your 10.12 skill builders in your Wiley homework. Thinking that a little bit better, and let's let's bring in some stereochemistry. We just focused on regioselectiveness. Let's focus on stereochemistry as well. So let's consider a radical halogenation that creates a new chiral center, or a halogenation that occurs at an existing chiral center. So here we have an example, 1, 2, 3, 4. This is a butane molecule reacting with diatomic chlorine in the presence of energy. We can see that the chlorine has added onto the chain at position 2 and in position 1. It's indiscriminate. You will have a mixture of both. But in the second position, this is now a new chiral center. That's an example of creating a new chiral center. And in the second example, halogenation that occurs in an existing chiral center. So let's use bromine in this example. Diatomic bromine in the presence of energy. And again, bromine is very selective, so we're looking at this position because that would be a tertiary radical. But this is already a chiral center, right? This carbon is attached to 4 unique items. That's what chirality is. You have 1, 2, 3 carbons in one direction, 2 carbons in the other, and 1 carbon coming up top. And of course, the 4th bond is a hydrogen. We just don't see it. When the bromine adds to an already existing chiral center, it still retains its chirality. Simply because the hydrogen has been replaced by the bromine, it still has 4 unique positions. Now let's explore the stereochemistry part of that. Here's our butane molecule, and I mentioned chlorine will add in both positions. Notice this carbon is not a chiral carbon in the primary position, but if it's at carbon number 2, we mentioned that this is an sp2. The radical is sp2, trigonal planar, so we can see the chlorine adding from the top or from the bottom, creating a dash or a wedge, a racemic mixture of both configurations. So a mixture of dash and wedge. And the same is true even for bromine. At a already existing chiral center, the bromine can add from the top or the bottom, creating a racemic mixture. But notice what's missing for the bromine is there's none of that primary position. Bromine is much more selective. They both will form stereoisomers. Chlorine and bromine both form a mixture of configurations, but chlorine will also form, in a pretty good yield, the first or primary position as well. And if there's a chiral center in that molecule that's not involved in the radical halogenation, so let's just take, for example, to illustrate this, we have a 5-carbon chain. At position number 3 is a chiral center. Position 3 is attached to 4 unique groups. The bromine adds to this, we'll call it carbon 4, and we produce a new chiral center. But notice here, this configuration didn't change. That's not what involved. And if the bromine then adds as both a dash and a wedge, these are not enantiomers. They are not mirror images of one another, but they're called diastereomers. In other words, they're not the same. So not a mirror image at all. Kind of like a cis-trans. They're stereoisomers, but not a mirror image. So if a chiral center, whereas these are mirror images, these are called enantiomers. These are mirror images, and that is because there was no original chiral center first, right? It added on to the chiral center. If there is already a chiral center that's not involved in the radical bromination here, you're ending up with diastereomers, not enantiomers. Let's practice that a little bit. Predict a stereochemical outcome of a radical bromination of the following alkane. So we have a cyclohexane, a 6-membered ring. We have methyl groups at position 1, 2, and 3, at position 1 and 3, and we also have an ethyl group at position 1. Sitting on the arrow is molecular bromine, and H nu represents energy to break the bond of bromine and form a radical. So that's the initiation step, is to break that bond and form bromine radicals. Decide the location of where bromination will occur. Where is the most stable radical by breaking a CH bond? Well, position 1 has carbon that's attached to 4 other carbons. It doesn't have any hydrogen at all, so it's off the plate. And so when I'm redrawing, this side of the molecule will remain the same. So we have our methyl group as a wedge, the ethyl group as a dash, and nothing else has changed over there. The most stable configuration for the radical is over here in the tertiary position. So I'll add the bromine in both directions. It would add as a dash, and it could also add, this is just all the original, that's going to come down more. And over here then, if the methyl ends up as the dash, the bromine will be the wedge. And so there we just have both enantiomers form. And so we notice here that the place of attachment, the most stable radical, would be the tertiary position. The bromine added on to that position both in the dash and in the wedge position. And you'll see many practices like this. Predict the stereochemical outcome of the radical bromination of the following alkane. So this is one from your homework, a skill builder. Think about what you'll see on the arrow, molecular bromine and a little bit of energy to create the radicals. Where do you see the most stable configuration for the radical to form? And I see it right here, where a tertiary radical would occur. And so therefore, bromine being very selective is not going to add in any other position other than the most stable configuration. So we will have a mixture where the methyl group remains as the wedge, and the bromine then could add as the dash. And in the same token, you'll have the second choice, where the bromine could be the wedge, and the methyl group end up as the dash. And let's pause our lesson here, and we'll pick up with allylic halogenation in a third video lesson. You're doing great. Take a break.